last time. So we're in the midst of this definition here, when I think we ran out of time because I thought I had more time than I did and I wasn't paying attention or something. I don't know. Ever happened to you? Time just flies when you're doing math, right? Okay. So if we have a central angle that we'll call theta, that's measured in radians, in a circle with radius r, then the length of the intercepted arc, s, is given by the equation s is equal to r times theta. The alternate version here is if this is degrees, then what has to happen? We'll measure back to radians, which means that I multiply it by pi over 180. So you see that the degrees version here is the same as the radians version, just we've multiplied the radian version equation by that conversion factor, pi over 180. Is everybody okay there? So let's do a couple of just quick examples to kind of get used to this or using this little formula. And then we'll scoot on to something else. Okay. So we're asked to solve for s if r is equal to 3.8 and theta is equal to 40 degrees. How do I decide which equation I'd want to use here? Kristen? Yeah, since my angle measures in degrees, I want to use the degrees version. And I forgot to write a unit down for this. Let's say that was inches. So when I type this stuff all into my calculator, I get approximately 2.653 inches. So just FYI, the unit on my arc length should match the unit for my radius. How's that feel? Pretty easy, I hope, right? Just pick the right formula and plug the numbers in. What if we ask instead, so here we're asked to solve for r if s is equal to 18 centimeters and theta is equal to 2.13 radians. So which equation would I want to use here? the first one, because theta is in radians, I'd want the radians version of my equation. So we know S is 18, we're looking for R, and theta is 2.13. So when we divide both sides by 2.13, we get 8.451 centimeters. Again, my unit should match the length unit in the problem. Is everybody okay there? Okay. Okay, so we have that a car has an 18-inch diameter tire and travels at 15 miles per hour. And we ask how many revolutions per second are the tires making. Does this sound familiar to anyone? Did you guys do the bike project last year? No. Well, never mind then. Okay. So this is, I'm just going to treat as a unit conversion problem. So I need to convert this rate of miles per hour into this rate of revolutions per second. So I can rewrite miles per hour as 15 miles per hour as 15 miles over 1 hour. So one thing I want to do is I want to convert my hours into seconds, right? So I know that 1 hour is 60 minutes, and 1 minute is 60 seconds. Everybody okay there? Next thing I want to do is I want to convert miles into revolutions of a tire. So how far does 1 revolution of the tire take us? So 1 revolution is just going to be 1 circumference, right? If I take my tire and I turn it, the distance I've traveled is the entire circumference of the circle, right? Because every point on that circle touched the ground as it made 1 revolution. Does that make sense? What's the issue, though? The circumference that we're going to have is going to be in inches, and my unit currently is in miles, right? So before I can make that conversion of distance into revolutions, I have to get the distance down into inches. Or I could do inches into miles, but I think it's more natural to go miles down to inches. So I know that 1 mile is 5,280 feet. I know 1 foot is 12 inches. And I know that 36 pi inches is 1. Yes, Teresa. Oh, goodness. Yep. So that should just be 18. Thanks, Teresa. Good catch. I appreciate you jumping on it before we had a chance to get too far down the road and really make a mess out of this. So again, if you see me making a mistake, even if I don't see you like trying to get my attention, just interrupt. So you did the right thing there. Okay, so now let's see what happens. So let's cancel some units here. And we see that the units that I'm left with, revolutions over seconds. And now I can just type this gobbledygook into my calculator to spit out my answer. If my calculator app wants to load, because sometimes it wants to be slow. Anytime you want to open Wabbit, about time. Goodness gracious. All right, let's shrink that down so I can see what I'm doing. So I'm just going to type this in one fraction. So I have 15, and I'm not going to times ones in the numerator. And in the denominator we have 60 times 60 times 18 pi. So I have 4.669 revolutions per second. How's that feel? It's okay? It's basically just a big unit conversion problem, right? The only thing that might have been novel to you guys would be this observation that 1 revolution is equal to 1 circumference. That was maybe not super obvious until I pointed it out, and then you're like, oh, sure, probably, yeah, that makes sense. But coming up with that the first time is kind of tough. Okay. That's it for section 1. So about trig functions of acute angles. This is basically the trigonometry that you did in your geometry course. So if you remember way back to the beginning of class, we talked about one of the first things we're going to want to do is take the definitions for sine, cosine, and tangent we had in geometry and extend those definitions to apply to situations outside of a right triangle. So that's kind of where we're going to start today. So we're going to start with these definitions, and over the next few lessons, we'll work on kind of extending those out so that we can deal with situations that we could not have using the previous definition. Okay, so let's start with the basics. Let's say we have our right triangle. And I'm going to specify this angle as theta. And actually, let's give these guys vertices some names. So relative to my angle theta, which side is the side we'd call opposite? CA. Good. So again, the opposite side is the one that doesn't make up the arms of the angle. And so which side is the adjacent side? AB. Good. Remember, the adjacent side is one of the two arms that make up the angle, but it's the shorter of the two arms. And then the hypotenuse, we know, is the longest side of the triangle, or the longest arm that makes up our angle theta. Everybody's okay with that? So from your geometry class, you probably remember that sine is opposite over, that cosine theta is adjacent over hypotenuse, and tangent theta is opposite over adjacent. We had an acronym that we used to kind of help us remember those definitions. That was Sohcahtoa. So again, that stands for sine opposite over hypotenuse, cosine adjacent over hypotenuse, CAH, and then tangent opposite over adjacent, TOA. You guys remember? Yes, Elizabeth? That's the Greek letter theta. Typically we name in geometry and trigonometry, typically we name angles with, or angle measures with Greek letters, and we use our standard English letters for side lengths. So this circle with the line through the middle is the Greek letter theta. Okay, so something that always bothered me as a student here, we have sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, but there's like 3 other ratios that I could write here. Why don't I have one for like hypotenuse over opposite, or hypotenuse over adjacent, or adjacent over opposite, right? Those are all valid ratios I could write. How come I don't have a function associated with those? Well, we do. We just didn't tell you about them in geometry. So we also have cosecant theta, which is hypotenuse over opposite. We have secant theta, which is over adjacent. And we have cotangent theta, which is adjacent over opposite. And again, we'll spell those for you, as I assume that this is maybe the first time we're hearing some of these words, or at least for probably most of us, the first time we're seeing these. Oftentimes we refer to these as reciprocal functions, because if you notice, the relationship between sine and cosecant is they are reciprocals, right? It's the same ratio but flipped. Similarly with secant and cosine are reciprocals, and tangent and cotangent are reciprocals. Okay, so Josh, you said something, but it was kind of quiet, and with the mask I couldn't understand you. Can you speak up a little louder?
Yeah,
COT. Yep, cotangent, so COT. Yep, again, perfectly reasonable thing. I know my penmanship is not like top caliber, so if you can't read something, particularly if it relates to a mathematical symbol that you know is going to be really important, perfectly reasonable to ask to double check on like what a letter is or what a symbol is or any of those things. So no problem doing that. Again, important that you understand. And if you don't know what the symbol is, it makes it hard to understand, right? Okay. Let's do a little example here to practice using these. So let's say we ask you to find the exact values for the 6 for theta in the right triangle that we've given. And I guess let's put some letters on the vertices here. Okay. So the first thing that I would do here is I would want to make sure that I've kind of labeled my opposite and adjacent and hypotenuse relative to this angle theta. So which side is the opposite side relative to this angle theta? AB. And the adjacent is? This is AC. Now it appears that we're missing a piece of information here, right? What piece of information does it appear that we're missing? The hypotenuse. How would we go about finding that? We can, since this is a right triangle and we know 2 of the sides, we can use the Pythagorean Theorem. So we know that a squared plus b squared, where c squared is the hypotenuse. So 5 squared plus 2 squared is equal to 29. So c is the square root of 29. And because the problem is asking for an exact value, I'm not going to convert the square root of 29 into a decimal. I'm just going to leave it as a radical. Is everybody okay with what I did here? Okay. So now I can just go ahead and use my right triangle to determine the values for sine, cosine, tangent, cosecant, secant, and cotangent. Sine is opposite over hypotenuse. But this isn't the typical way that we want to leave our final answer, right? What's wrong with this form? There's a square root in the denominator, right? How do we fix that? We rationalize the denominator, multiply the top and bottom of that fraction by the square root of 29, the conjugate term that we use there. So I'd really say my final answer is 5 square root 29 over 29. For cosine theta, what would I say that is? Two over the square root of 29, but I would need to rationalize the denominator there again. So I'd end up with 2 root 29 over 29. Okay. And then what about tangent? Five over 2. Good. Now for cosecant, secant, and cotangent, I have 2 options, right? I could use the definition for cosecant and say it's, okay, this is hypotenuse over opposite. Or I can observe that it's going to be the reciprocal of sine. So I could take a look at, say, this part of it and write it as the reciprocal. Or if I wrote it as hypotenuse over opposite, I would get the same result. Either way is fine. Everybody okay there? Okay. Secant is going to be the reciprocal of cosine, or hypotenuse over adjacent. And cotangent is going to be the reciprocal of tangent, or adjacent over opposite. What do you guys think on that? Hopefully that was pretty easy, right? We just had to use some definitions. Now, these new ones that you might not remember the ratio for, you would want to have those memorized. Okay, so secant, cotangent, cosecant. You will want to have those ratios memorized. That will be helpful. Trigonometry is a very much like geometry, requires like a lot of remembering of past results and formulas and relationships between things. And while I wouldn't require you to memorize all of the things, I think that life gets easier when you do have a lot of the pieces memorized, so you're not having to like break your train of thought and go and look things up all the time. Many of you guys probably remember from geometry that once you started memorizing some of the theorems in geometry, doing the proof was a lot easier when you had the theorems in the top of your head versus like going back and having to stop your train of thought and look things up all the time. That once you kind of got those theorems memorized, things moved much smoother. The same kind of thing will be true in trigonometry. There's a lot of kind of like theorem and definition and fact that we're going to probably end up memorizing along the way. I won't require you to memorize all of it, but I think life gets easier when you do memorize a lot of it. So I'll try to point that stuff out to you as I go. Okay, let's do another example to just kind of Okay, so let theta be an acute angle in a right triangle. If sine of theta equals 1/3, find the other 5 ratios for theta. So I would start by drawing a picture. So here's my right triangle, and I'm going to label one of the angles theta. It doesn't really matter which angle you label. Now I'm going to use the fact that sine is opposite over hypotenuse to determine the side lengths for this opposite and hypotenuse side of my triangle. How would I find the adjacent side? Pythagorean Theorem. So a squared plus b squared is equal to c squared. Remember that c squared is the hypotenuse. So b squared is 8, or b is equal to 2 root 2. So I reduced the square root of 8 just in my head there. Does anybody need a refresher on how you do that? Okay, fair enough. If you change your mind later, we can always go back and talk about it again. So there's my adjacent. So now I have everything I need, right? We knew already that sine was 1/3. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent, but we should rationalize. And then we can do the other ones. So cosecant is the reciprocal of sine, or you could think of it as opposite or hypotenuse over opposite. Secant is the reciprocal of cosine, or you could think about it as hypotenuse over adjacent. And cotangent is the reciprocal of tangent, or you could think about it as adjacent over opposite. Is everybody okay with what we did there? Again, not tremendously different than the previous problem, right? So what if we asked you now to find the exact value of sine of 30 degrees? Now, ordinarily, we couldn't ask you to find the exact value of just any old angle here. But the fact that this is 30 degrees is critically important. Allows this to be possible. From geometry, the 30, 60, 90 triangle, that was a thing, right? We remember at least the name of it. Okay. So the ratio of side lengths in a 30, 60, 90 triangle, the short side is x. The medium side is x square root of 3. And the long side is 2x. So using that, then sine of 30 is going to be opposite over hypotenuse, which is just 1/2. This is something, again, that you will want to have like memorized. Again, we'll use this quite a bit here in the next chapter too. So that's one thing that at one point you probably remembered or had memorized just about in your geometry class. Now it's been 2 years or whatever, so I don't realistically expect you to still have it memorized. But I would hope that you could reacquire it pretty quickly, having at one point probably had it memorized, right? There was another special right triangle. Do you guys remember what that one was? Yeah, 45-90 triangle. Very good. And for that one, the ratio of side lengths, the legs were x, and the hypotenuse was x root 2. And similarly, with the 30, 60, 90, that's going to be one that's useful to have memorized. At least particularly for these next chapter too, where we really use these a lot. What if we ask you to find sine of 17 degrees? Notice I'm not asking for an exact value here. How would we find sine of 17? How did you do it in geometry? Put it into your calculator. That's absolutely what I'm looking for here. That's exactly what you would have done. What's the one thing you have to be careful about when putting this into your calculator, though? Yeah, I want to make sure that the mode is correct. What happened here now? There you go. Okay, so to check that, we'll press the mode button right next to the second button. You notice that my calculator is in degree mode. If yours is not, just move your cursor so that it's on the degree, the word degree, and press enter. And that'll change it so that it's in degree mode. Once you do that, it'll stay in degree mode unless you reset your calculator or change it yourself. So I'll exit back out of here, and we'll just do sine of 17. So 292. Everybody okay there? What if I asked you to find 8? Do I have a secant button on my calculator? No, but we're going to take advantage of the fact that we pointed out earlier that secant is the reciprocal of cosine. So how am I going to type that into my calculator? Well, I'm going to do cosine 78, and then I'm going to use this reciprocal button that's right below the math button that has the x to the negative 1. So that's 4, 8, 10. 4.810. I want to point out too that this is not the same thing as cosine inverse. Cosine inverse, the negative 1 exponent is located on the cosine rather than on the whole thing. If I try to do cosine inverse of 78, I'm going to get an error. Okay, so make sure that you're using the reciprocal button on your calculator and not trying to do cosine inverse or something. Okay? What else do we need to talk about here? Okay. This is probably the most fundamental problem to your trigonometry section in your geometry class, where we ask you to solve for a right triangle. What does it mean when we ask you to solve the triangle? Good. Find all the side lengths and all the angle measures. Excellent. So what do you want to start by finding? Great, let's find angle C. How would I find that? Okay, so I can do 180 minus 41, or you could just do 90 minus 41. Either is fine. So I have 49 degrees for angle C. Everybody okay there? And this was the triangle sum theorem, right? That there's 180 degrees, or the interior angles of a triangle add to 180 degrees. That was the geometry theorem that we used there, if you didn't remember why it's 180. And there's a corollary to that that says in a right triangle, you can just do 90 minus the other interior angle. Okay. Now let's solve for one of the side lengths. So to do that, we need to pick the angle measure that we're going to use. Let's say we're going to use angle 41. And then we want to pick the side that we're going to solve for. Which side would you like to solve for first? What? Okay. So CB, I'll call that side X. So looking at 41, CB is the opposite side, and the side we know is the adjacent. So I'm going to use which trig function? Good. Tangent. So say tan 41 is x over 12. And if I cross multiply tangent of 41, and if I type that into my calculator, I should get about 10.431. Everybody okay there? Okay, one more side to solve for. What do you want to do to find that one? Okay, so that's a reasonable thing to say. Is that going to give us the most accurate answer? I would contend no. I would say that there's a way to get a more accurate answer than using the Pythagorean theorem. Now, for most things in life, it's not a problem to do that here. But if you're like working for NASA and you're trying to like land a rocket on the moon, if you have a less accurate answer, you could miss the moon, even if it's only off by like something in the 1,000th decimal place, right? So depending on what you're doing, like a little bit of inaccuracy can make a big difference. Let's try to get the most accurate way of doing this. So I would say to do that, I would use angle 41 and the adjacent side. So here we'll use cosine of 41 equals adjacent over hypotenuse. And the reason this method is going to give us a more accurate answer is here I'm only rounding once, right? All of the inputs to this equation are non-rounded numbers. If I use the Pythagorean theorem here, I'm going to use a rounded answer. I'll do a calculation, and then I have to round my final answer again. Here, I'm only rounding my final answer. I don't have a second rounded number involved. So it's going to give me a slightly more accurate result. Now, depending on the number of decimal places we rounded here, I rounded 10.43 to 3 decimal places. If you use the Pythagorean theorem, it's probably going to be accurate out to 4 decimal places, which is probably good for most anything you would be doing practically even in a like scientific setting. But why not be careful, right? If you can, it's no harder to do it this way. If we can get a slightly more accurate answer, I think that's worth doing. So when I cross multiply, I get y times cosine 41 is equal to 12. If I divide both sides by cosine 41, and then type that into my calculator, I get about 15.900. How's that feel for you guys? It's okay? You guys kind of remember doing that back in geometry? That was a very common problem, right? Solving the triangle. I know geometry was a long time ago, and I'm not expecting that you have like total mastery of it. That's why we're doing some examples and kind of talking through things again. So the next section here is about angles of rotation. And this is a really kind of critically important idea moving forward. So really up until this point, we didn't have a way to define any angles that were, say, bigger than 180 degrees, right? Even in geometry, if you tried to draw like a 100 or a 200 degree angle, you would draw something like this, like that's 210 degrees or what. But we never really drew it in that direction, right? You would just talk about this angle being 150 degrees. You always defined your angles like with the concave part of the angle, right? Do you guys remember that from geometry? So what we want to do here today is come up with a system where we can define these bigger angles, and we can define even things like negative angles with this new system that we're going to develop right here, right now. So what we're going to do is we're going to embed all of our angles into the xy axis. We're going to fix one arm of the angle onto the positive x-axis. We're going to call that the initial side. And we're going to fix the vertex of our angle at the origin. And now the other arm of our angle, we're going to allow to rotate around the xy axis in a counterclockwise fashion. So if we have theta equals 210, we'd have 90 degrees to here, 180 degrees to here, and like 30 degrees more puts us here to 210. We call this other arm of the angle the terminal side. Is everybody okay with this so far? So using this, we can draw things like a 570 degree angle. Let's do that real quick. So here's our terminal side. 90, 180, 270, 360, 450, 540, and 30 degrees more. Is everybody okay with how I did that? How do I know each quadrant is 90 degrees? Because the xy axis meet at a right angle, right? Not anything super tricky there, right? Take a moment, look at these two angles that we've just drawn here. What do you notice about these two angles? Specifically the picture. Kristen? Well, they both ended in the third quadrant, sure. Where in the third quadrant did they end? At the exact same location, right? This little spot here was like 30 degrees. That little spot there was 30 degrees. Here, the angle, the picture of the angle is identical, right? The initial side is at the same location. The terminal side is at the same location. These are essentially still the same angle, even though they have different angle measures. We have a word for this. It's called coterminal. So coterminal angles are angles with different measures, but the same initial and coterminal side, or I'm sorry, initial and terminal sides. So what if I want an angle that's coterminal to 40 degrees? How would I find that? Teresa? Yeah. So 360 degrees is going to spin that around one full rotation, and you're back exactly where you started, right? Okay. What if I wanted another coterminal angle? What's another angle coterminal to 40 degrees? How would I find that? Okay, you want to subtract 360? Sure. We haven't defined what a negative angle means yet, but that's on the to-do list here in a second. How about another one? What if I add 360 twice? Would that get me coterminal still? So if I want a coterminal angle, any of those would satisfy, right? What if instead it was a radian measure? What would I be adding this time? Or subtracting? The question becomes, what is 360 in radians, right? So if I just do my quick little conversion from degrees to radians, 360 degrees is the same as 2 pi radians. Is everybody okay there? So here I'm just going to add 2 pi. So I made a common denominator and added those fractions. Does anybody need a refresher on how we add fractions again? What if I wanted another coterminal angle? Well, I just add another 2 pi, right? Everybody's okay there? And I can do that as many times as I want. You guys agree? Okay. Let's talk about what we mean by a negative angle. So if I want to draw a negative 160 degrees, I'm going to start the same way. So here's my initial side. But instead of rotating counterclockwise, we're going to rotate clockwise. So 90 and then 70 more puts us over here for a negative 160 degree angle, which is the same as a positive 200-degree angle. Those two angles are coterminal. Everybody okay with that idea? Okay. So this is actually like a really important skill that you're able to competently like draw these angles and get them in the correct locations. So just whatever you have handy in your notes or your tablet or whatever, just off to the side, let's give you guys a minute, let you draw some pictures, and we'll kind of go through them together, okay? So just wherever you're at in your notes or on a scrap sheet of paper or off in the margin somewhere or whatever you want to do, let's try to take a minute and draw these two angles, and then I'll go through and draw them afterwards and kind of talk through what we're doing. But this becomes a really important skill that if you don't have this skill, things get pretty hard and confusing if we're not able to draw these pictures. So taking a minute or two here to practice is not a bad thing. Yes, sir. Of course. Mm-hmm. There's what 780 should have looked like. You should be in the first quadrant, or the angle that you make with your terminal side and your initial side would essentially be 60 degrees. So to do the radian one, let's try to do this without having to convert anything into degrees. I know that radians feel uncomfortable, and that's okay right now. So 90 degrees is the same thing as pi over 2 in radians. And I'm going to think about 10/3 as really 3 and 1/3. So I'm going to do a half, 1, 1.5, 2, 2.5, 3, and then a third. So I should be somewhere in the third quadrant, more than halfway, because a third is more than a quarter. Everybody's okay with that idea? So this angle here should be pi over 3, which coincidentally is also 60 degrees. What do you guys feel okay about drawing these pictures? Okay. Again, if we need to do some more practice on this later as we get going, let me know and we can always come back and do some more. Okay? All right, our last section in chapter 2. What? Yeah, I'm serious. There's 4 sections. Is now combining these 2 ideas. So we just developed this angle of rotation, and now we want to somehow redefine like our sine, cosine, tangent, cosecant, secant, cotangent in such a way that we can apply those definitions to things that are angles of rotation. So we're moving away from the right triangle and using an angle of rotation instead. So to do this, what we're going to do is we're going to try to merge those 2 ideas together. So here is my angle theta. Okay with this? And I'm going to pick some point on the terminal side of that angle theta that I'm going to refer to as xy. Everybody's okay with that? What I'm going to do now is I'm going to build a right triangle using this point xy. So I'm going to draw a line straight down to the x-axis and then straight over to the origin and then back to the point, which makes my right triangle. Is everybody okay there? What's this side length of my right triangle? X. Very good. Because the point is xy, we've gone x over. And then what's the other side of my right triangle got to be? Or the other leg, I should say. It has to be y. And then what's the hypotenuse got to be then? Square root of x squared plus y squared. Right? Just the Pythagorean theorem applied to the 2 sides. We're going to refer to this side as R. So, if I do this, and I want to say calculate sine of theta, well, sine is going to be opposite, which is y, over hypotenuse, which is r. Similarly, cosine theta is adjacent, which is x, over hypotenuse, which is r. Tangent theta is opposite, which is y, over adjacent, which is x. Cosecant theta is hypotenuse, r, over opposite, y. Secant theta is hypotenuse, r, over the adjacent, x. And cotangent theta is adjacent, x, over opposite, y. So again, remember, in this situation, xy is any point on the terminal side and r is the distance of that point to the origin. So we've now taken our definitions of sine, cosine, and tangent that were locked in to right triangles, and we've extended this definition, so instead it's applying to a point on the terminal side of an angle of rotation. It's a big change, guys. Congratulations to us. Let's do a quick little example. Okay, let's say the point -3, 4 lies on the terminal side of theta. Find the 6 ratios for theta. Well, the first thing I want to do is calculate r. So r is just the distance from that point to the origin, or just basically x squared plus, or the square root of x squared plus y squared. So that's the square root of 25, or just 5. Everybody's okay there? Okay, so sine is y over r. So in this case, that's 4 over 5. Cosine theta is x over r, so that's -3 over 5. Tangent theta is y over x, so that's 4 over -3. Cosecant is r over y, which is 5 over 4. Secant theta is r over x, which is -5/3. I guess you could put the negative sign on the 3 also. It doesn't really matter where the negative sign goes, right, guys? If you got a negative sign in the fraction, it's the same whether it's on the top or the bottom or out front to the whole thing. And cotangent theta is we're doing that first, is x over y, which is -3/4. Is everybody okay with this idea? Let's stop here. We still have quite a bit more to do here in this section. But let me make a little note of where I left off at. You guys will have to help remind me, because I'm sure I'll forget between then and now, or now and then. Just as a heads up, we've done a lot today. So there's a lot of problems from the homework set that you guys should be able to do at this point. So if I look at this, it looks like we could do up through 46. Hi, Miss Anderson. Okay, I'm sure I have it laying around in my pile of things somewhere. Okay. Does that feel okay with you guys? We'll stop here. That's enough. We did a lot.